Right, yeah. So, yeah, firstly, a couple of questions, if I may, about the sample. I have it over here under the microscope at the moment,
Okay.
the just an optical microscope, and then I'm going to do some incredible macro photography using a Sony A1 and a macro lens because I need to merge the two. I had a bit of a disaster on the SEM yesterday, but I'll talk about that later.
Okay.
Nothing to do with the damage to the sample, but damage to the things that are captured. But I have a couple of questions. You answered some of them in your original letter. So you're using a particular type of aluminum stock, aluminium stock, as I call it, being English.
Right.
And you said it's 6061-T6 type aluminum alloy, yes?
Yes, that's the one I'm using.
Okay. And could you send me the data sheet for that? Is that possible, or is it just something I
Certainly.
can easily find online? I just want, from the actual source that you got it from, rather than potentially a sort of generic source.
I could find it. I'll just have to search for it. It was produced by K&S Metals.
Right.
That's the manufacturing company. So they do have publicly available details of that alloy. And
Okay. If
I'll
you
send
can
that
send
to you.
me the particular reference to the site where that came from. Um,
Okay.
Typically with aluminium, like unless it's a five nines piece of metal, it's going to have quite a few impurities in there. Typically, you get silicon and magnesium and iron, and for certain, there was iron flecks in there. Now, I could see that you cut the button, as you called it. Uh, did you cut it with, hacksaw or a Dremel or what did
So
you cut?
that was fabricated by a colleague using a CNC machine. I could ask him the details of that.
Okay,
As
yeah. And when you produce that, like, are you uh, do you know what the cutting fluid is? Is it cut in water? Is it cut with oil? Is it cut with, I don't
I
know.
believe it's water. I could call him after this call
Okay.
and he could
Yeah.
provide me the details.
Yeah, because it seems relatively um, less contaminated on the edge and on the cut line. There's clear steel in there, and I'm wondering what bits were used in terms of the cutting, because it it could be that it was using a tungsten carbide cutting tool, because I see fragments of tungsten in there, which that might be something that was used to cut it. I don't know.
Okay.
Sometimes you can get like a steel bit that's hardened with tungsten carbide or something.
Right. And he does use those types of bits on other pieces of equipment, but as far as I know, it was water that was used as a cutting fluid, but I'll ask him. I'll
No,
be
but the
certain.
actual cutting tool.
Yeah, the tool itself that I
Oh,
believe,
actually cut with water.
yeah, he used water as the fluid, but the cutting bit itself, I will have to ask him, but I do know that he uses tungsten carbide bits with other pieces of equipment and
Okay,
other
because
machines too.
I initially, when David said, I was mentioning that there was a mark on the other side, and David said, "Oh, that's where it's welded or attached to a piece of tungsten." And then in your letter, I note that you say that's actually a piece of nickel.
It's nickel. Yeah, that small square piece is a piece of 99% pure nickel that's fixed to a 18 gauge nickel wire.
Right. Okay. So there was just some discrepancy between the understanding there. So the nickel, do you know the impurities in that?
As far as I know, it's claimed to be 99% pure. I
Right.
could provide the manufacturing details of that as well.
Because of course you've got plasma going around in there, and that can pick up ions of almost anything that's available
Definitely.
in the environment. So we kind of have to discount that. Um, yeah, and did you use any kind of solder to attach it to the back, the nickel to the back
I
of the?
did not. I used a spot welding process that just adhered the metals together.
Okay, right. That's interesting. So did you have the two electrodes either side of the aluminium.
That's correct.
Right. So I need to know what the, oh, that's very interesting. That might change everything. Hmm.
Yeah, I see the point being made. The electrodes on the spot welder, they were 99% pure copper.
Right.
That
Okay.
also I could provide. Yeah.
That is where some of the copper may be coming from. Okay.
Okay.
All right. That would explain it. Okay. Um, yeah, and then what else is in the copper? Okay, that's interesting.
Yeah, that could pose some impurities.
Yeah, it's worse than that.
Okay.
Um, yeah. Oh, that's really highly unfortunate. Hmm. Yeah, that's put me in a. I've trailered something to
Okay.
discuss these materials, and I didn't. Because there is some silver and tin um on the surface. I suspected you might have. How do I kill this stupid center stage? I'm not moving my
Oh no, I
laptop.
noticed it's automatic.
Yeah, I'm quite capable of framing myself. Let me see if I can get rid of that because it's a little bit. It's just a new laptop and it keeps doing it. It's a bit tedious. Um, camera, camera options. There we go. Okay. Sometimes what? That doesn't look like. Okay. All right, maybe if I don't move my head and it won't try and follow me. Um, okay, so right, that's interesting.
Because that led you to the idea that I was using a solder of some sort as a
Yeah,
blinding
because
agent.
well, but of course, if you're not using absolutely brand new copper spot welding,
Right.
then the surface I'm analyzing um, could be contaminated with every other piece of metal that's been spot welded using
So
that spot
in this
welding.
case, I recall exactly the fabrication of that electrode that was placed inside that tube. Those were new electrodes on the spot welder
Okay,
because I usually change them out every time I adhere a piece of nickel to a new electrode. So those were new spot welding probes. But nonetheless, like I said, I could bring the manufacturing information on that copper, and I'll provide that to you as well.
where is the spot welder?
It's in the shop. I'm
Which,
away from it right now.
but do you go there daily?
I usually do, yes.
Could you video the typical process you use with as close framing as possible on the actual spot welding?
Okay. I
Um,
can provide
just a
that.
smartphone video, but like right up as close as you're willing to get the camera without worrying about it being shot by bits.
Okay. Yeah,
Yeah.
I mean, it doesn't produce a nasty spark of any sort, so I could be very
So
close to it.
describe how it visually appears to you.
What exactly the process, the actual
I know what
spot
spot welding
process?
is, but like there's
Okay.
variations in current and I mean obviously you're
Right.
yeah.
So typically, a decent current is applied between two copper electrodes, and of course, the electrode itself, the aluminum electrode, is placed, it's sandwiched between a small square of aluminum, and the electrodes go on either side. And just for the duration of 1 second, there's a couple tens of amperes that flow through that looped circuit, which ultimately melts and adheres that nickel to the aluminum
Yeah.
on one
So
side.
so just can I clarify? You've
Yeah,
got the aluminum disc, and the nickel with the bent electrode contact piece, and you've then just got the two coppers that pieces that are electrodes that are pressing those two pieces together, and the current
right,
is supplied through that.
right.
Okay. Now, typically, when you look at the electrode after it's been spot welded, do you see anything on the surface of the aluminium side that is going to be the single point electrode for the tube?
Usually there's a very minute dent or a pitting that occurs from the aluminum melting itself, just ever so slightly. That's really the only sign of any tarnish or any noticeable maldeformities.
Okay,
Are there colored?
this
Yeah.
helps me because
Oh yeah.
I noted that on the center of the electrode, which I imagine is where you're trying to, because there's damage on the backside, which I guess is where the nickel would be attached, and then there's
Right.
damage on the ion bombarded predominantly side, and it's actually in the center of the electrode. So I imagine if you're trying to bind it through the center of the disc, you would have the two electrodes connecting around the center point. Is that correct?
Yes, that's correct.
Okay.
So whenever damage occurs on the nickel side, usually it mirrors on the other side of the aluminum, which is, in the direction of the beam with inside the tube.
Yeah. Okay. So I was trying to explain to myself
Mhm.
why I was seeing some features in the center of the electrode where the bulk of the arrangement, of the spatial arrangement of what I think is a very interesting feature, um, is on the bulk of the electrode, as it were, rather than just in the center section. So there's a, I'm just looking at it now. That Yes, I'll pull it out. Now it's following me and I want it to. Right. So yeah, I see there's a, yeah. Um, uh, um, hmm. But it tends to just look melted, but basically aluminium, yeah?
Yes.
Okay. All right. And how long did this electrode run for?
About 50 continuous hours over the duration of multiple days.
Have you tried any other ways to attach the electrode to the back?
I have, by physical means without any form of spot welding. It's rather unsuccessful because the electrode, during its bombardment process, heats up to a rather significant degree, and it does require physical melting to be secure and pretty much withstand those temperatures. Otherwise, no other means can suffice.
How long does it take to get these kind of marks appearing on the electrode?
During the spot welding process or the discoloration after
The
use.
discoloration after use.
That I would say following it varies between 9 to 10 hours, 9 to 15 hours of continuous use. That, of
Oh,
course, corresponds with the pressure within inside the tube and the overall geometry of it as well. That has a significant impact from what I've noticed.
have you monitored the pressure of the tube during operation?
Not physically, because imparting any electrodes, any physical measuring devices on site on the actual tube itself would dampen its performance from what I've noticed, but also lead to a differing outcome in the production of the type of X-rays that the tube inherently produces. So I do have special vacuum systems, ion gauges, and what have you to measure that, but when I have done that, it severely impairs the operation. But based on the color, I could assume that the pressure does increase. The vacuum level increases because the electrode and the other metal bodies act as getter elements which absorb contaminants,
Yeah, yeah,
hence
yeah.
their discoloration
Have you
as well.
considered, as is the case with many old tubes, I'm sure you're aware of actually having a getter in there of some kind?
Yeah, so I have also considered introducing a sacrificial piece of, let's say, aluminum, or I'm hesitant on using any other heavy metals, not for health reasons, but for the type of X-ray produced, that it would suffice as a getter, but so far I have not had any success in really reducing the problem of this oxidation that occurs on the electrode and subsequently dampens its effectiveness. But
So,
it is
yes,
a project in
you're
progress.
saying that you think it's oxidation on there.
Yes, by absorbing the contaminants. The reason I say that is because on other research vacuum chambers that certain universities produce, and work with, I've seen the same type of discoloration occur on the inner lining of their samples and chambers, which is reminiscent of the electrode, but of course I cannot be so certain of that.
Okay. I guess I really need to see a unit that has just been made and not run
Okay.
because I need to understand. You see, there is a chance that what I've seen on here could be caused by the spot welding process itself.
Okay.
Um,
If possible, I mean, I have a plethora of unused electrodes that have not been spot welded. I could send you a
yeah,
couple.
we need to find a better way of sending it. The package got stuck in customs for
I
quite a
saw,
period of
yeah.
time, which is laughable for such a small thing. Um, if it's okay with you, just cut off the excess on the the when you've got the wire attached, just cut off the excess of the electrode, so it's just the metal attached to the back,
Okay.
and then just send it in a normal envelope, or
Okay, I could do
a
that.
thick card envelope, and just send it as a letter. Um,
Okay.
so that it's not a package. Packages just tend to get stuck here in customs, and you have to pay for them to be released. And even if they're valueless, they have to go through their processing, and
Right.
so they charge you a standard fee. And then if you don't answer it quickly, they charge you a daily fee on top of the standard fee for storing it, regardless of what it
Oh,
is.
that's ridiculous.
Yeah, yeah, yeah. So just send it as an envelope. Okay.
Okay.
All right, so I definitely need to look at and in fact, what I would ask is if they're not too expensive to make, could you send like two or three so I can do a comparison, like a statistical comparison between, this electrode and one that hasn't actually had done any runtime?
Yeah, of course I could do that. I'll send
Yeah,
you some.
yeah, because okay, so what happened yesterday is I did about 5 hour session, a 4 hour session on the microscope. It was a new microscope, and normally I have the microscope set up at this particular place with screen recording software and everything, and it just works flawlessly. Now, it's Phenom microscopes by Thermo Fisher Scientific, which is now moved on. It's absolutely brilliant instrument. However, the software tends to be in a permanent beta,
Oh,
and I I had done about 4 hours of analysis, and I was doing a tile map because it's a good way to get an overview of the whole electrode or the parts that I'm interested in, and then you can spot certain things by quickly zooming in and out using the deep zoom image format. Which
okay.
is kind of like Google Maps. You can kind of zoom in and zoom out and move around it really quickly. And I can possibly show you that if I can get it running on the Mac side of this, the PC side of this Mac in a minute. Um, but whilst it was building this deep zoom image, as I normally do, is just check whether I'm getting to see the areas because sometimes it's a little offset. And so I did some checking, and the software just crashed.
Oh,
And
just great.
and I it apparently saves the files in an open session on the microscope, which has its own computer in, and no one in the building knew how to access those files. So I lost all of the analysis,
Oh, that's a
but
shame.
I had it all on the video recording. But I'm just looking at um the flash drive that I was recording to. It would appear that I was saving the images there. The actual data and analysis goes on the computer in the thing, and you have to save it from that computer, and it copies it across. So that
Okay.
didn't happen. And I've just been looking now for the video recording because I thought I was sort of sweet. It doesn't matter. I've got all of the data, and I actually do this like no one does this bar me, but like I do it as a backup in case the worst happens. And I
Okay.
haven't actually got it on here, so I thought I'd set up a directory on here for it to record to, but it must be on the computer there. And I've only just found this out just before I was calling you, because I wanted to show you through the data. So, and when I set it up, I must have made a directory on the local computer there. I really hope I did, because it certainly didn't complain about it recording. And normally, if it had nowhere to record to, it would say. So it
Right.
recorded somewhere. It just didn't record on my device, and I'm absolutely gutted because I need to fix this and I hope someone's there and it's going to be a fairly big file because you can imagine 4 hours recording. Okay, it's H.264, but it's 4 hours and it's recorded
Yeah.
um, at 1440p at 60 frames a
Oh,
second. So
rather it's
it tends to be in the tens of gigabytes. So like uh, I might just have to take a 6 hour round journey to Prague to go and get it again, which is just it's highly tedious.
I could imagine.
But the putting this question of about whether the spot welding could have done what is observed, and there is a potential that it might have done, and in that case, it's interesting in its own right, and I'll tell you why in a minute.
Okay.
Um, Essentially, it looks like the process of low energy nuclear reactions occurs through a magneto-hydrodynamic structure, which is fractal. It
Hmm.
is exactly the same shape as the Wardenclyffe Tower, and is exactly the same shape as the geometry of the Great Pyramid of Egypt.
Okay, I see.
Um, and your overall blemish on there, I could see it with my naked eye. I just took out the camera and I started videoing it, and I'm looking at it under the microscope. I can see it. I know what I'm looking for now because I've seen so many of them
Right.
over so many years. It's just like, couldn't be. It looks like it is, and it looks like it is. Um,
Hmm. Interesting.
so So it has these kind of two triangular bits that point in, and depending on the overall structure, they can be further apart. And the triangular bits point up and up and up to something. So I've seen it on various reactors. So I was quite excited to look at it. And on one side, it has typical stellar synthesis of elements,
Hmm.
and we get this in cavitation. Um, we get this in nickel deuterium oxide and diamond reactors. And um, to cut a long story short, the etheric matter rays that you're seeing. So like, and I have Jerry Vassilatus's book here, and that's the first time I was exposed to the work of Tesla from this period.
Oh,
Um,
yes, he's a very decent author.
yes,
His Endiums, I believe, right?
yeah, yeah. So I read the one on. In fact, I made a big video of it 2 or 3 years ago or something on um, uh, Cold War technology. That book.
Oh, okay. Yeah.
Yeah. So he discusses that Tesla found that anything above aluminum was not suitable for producing clean etheric matter rays. He used beryllium, which no, I wouldn't want to go near anyway. Um,
I can see why, yeah.
Magnesium, which, if it's thick enough, it's fine. It doesn't ignite.
I
But
have had, sorry to interrupt,
go
but
on.
that when it comes to the actual composition of the electrode, I've had quite the play of experimentation with that and have can corroborate with Tesla's statement. So magnesium, it is lighter, but the problem is because of its properties, when it's within a vacuum and high potential is applied, it has a chance to sputter.
Yeah, it just
And
goes
its
over. It
life
covers the
is,
tube with stuff.
and any heavier electrode samples such as tungsten or let's say platinum, as Tesla used, the wavelength of the produced X-ray is shorter from my measurements, and it does impart, dangerous effects as I've been able to find on certain
So,
organisms.
so yeah, I can discuss where that's probably coming from.
Right.
Have you, and we'll come on to that. Have you tried using spectroscopy to see element changes over time?
I have not.
I would recommend you get yourself an affordable. I can point you in that direction. You can go and see it on our MFMP channel. Just
Okay.
it's a fairly affordable unit. It's in the hundreds of dollars and stuff. Um, uh, you can see this, and this is what the Sapphire Group did. This is what Ken Shoulders did. This is what Anatoly Klimov does in his plasma vortex reactor. It's an easy way to see spectral lines from particular elements as they're synthesized over time. Because you're
Okay.
saying it takes how many hours before it starts to discolor?
About 9 to 15 hours of operation.
Okay. Um, can you confirm with the person that's doing the machining, um, or can you confirm yourself what cleaning process is gone through with the electrodes once they're produced?
Okay. I'll ask him that.
And from your perspective, you don't do any particular cleaning.
I do not, other than just a very light surface cleaning using a solvent and acetone,
Okay.
mainly to rid the surface of any carbon residue that usually builds up also during the glass blowing process.
Right. Okay. So you blow the glass around the electrode, or you have to do
Yes.
some finishing work.
So the stem, the glass stem that it's attached to,
Yes.
that's built around the electrode. Usually during the annealing process of it, that's when carbon residue builds up, so that's when I clean it. But the actual envelope shape of the overall tube, the electrode is inserted into it, and then the seal is made around it. But as
Yeah.
far as any carbon, it's
So
only during
you're using a propane torch or something.
propane and oxygen.
Okay. Right. Um, and the glass, have you had that assayed for its elemental composition?
I could obtain that from the manufacturer. I know it's definitely borosilicate, but the specific type of borosilicate I would have to inquire.
Yeah, that might have boron oxide in it, but it might have also lithium carbonate in there as well.
Right.
And there's going to be some adhesion of gases to the surface on the inside as well. And unless you heat and evacuate for a long period of time, these things take a long time to, bake out, as it were.
Definitely. I do perform a bake-out process,
Right.
and what's interesting is that the residue that the contaminants, which are still adhered to the electrodes, as well as the inner glass wall, when I apply potential, they are not necessarily seen in terms of a plasma, but it does take a while for their presence to reach a full brightness as they become liberated from the surfaces and intermingle
Right.
with the vacuum.
Right. So, how familiar are you with my work and the project's work of the MFMP?
I'm not very familiar. I
Okay.
only I only know of you and
Mhm.
as well as the Fleischman Project Memorial Project
Mhm.
through David Boutier that has
Yeah.
been in contact with me for some time, but other than that, I seldom know
Yeah,
of
so I
any.
think what happens, I talked about that Jerry Vassilatos work, and then I think David found your work, and because he's got all the high voltage, high frequency equipment, he thought, well, I'm going to give this a go. And he contacted you, and he's found that he's tried to characterize the radiation, transmission and penetration and so on. In one of your talks, you talked about aluminium doing some partial or effective shielding. Is that right?
I have noticed that it's rather unusual that despite these rays being able to penetrate through open air for rather quite, vast distances, ordinary lead should not be able to block it, but it is. Very thin aluminum. I have the thickness written down in one of my notebooks that it's readily able to block it. And this is something that Tesla has attributed to the effect of these rays, and I have been able to corroborate that to some extent.
When they're pure etheric matter rays, yeah, but Tesla did also note that when they're dirtier, that like you use heavier elements than aluminium, he was able
Yes.
to feel pinpricks 15 feet away behind both dielectrics and conductors.
Yes, that I have not been able to experiment with because I do not want to work with at
Yeah.
all.
What kind of radiation monitoring have you got?
So I mainly have ionization detectors.
Right.
It's
What
fairly
kind?
limited. It's mainly for qualitative analysis. I have Navy issued ionization detectors. I have the numbers written down. I don't have access to it right now. I can
Mhm.
send that to you afterwards. But they were essentially used by the Naval Department in nuclear surveying experiments and other research projects that they were engaged in during their period of the 60s and 70s. All the equipment's calibrated so that it's accurate, and it's mainly used to see, what the intensity is over a specific distance rather than actually characterize the rays themselves to, the
Yeah, so
extent that
it's count rates, is it?
right. It counts.
Okay, that's actually fine. Now, have you tried this? Putting the detector behind the aluminium foil.
I have, and I have reported the decrease in detectable radiation that the counter experiences. And that is actually being reported in a small report that I am in the process of constructing because there are other details that are still being left out that I need to experiment further in, with the
Have
help of
you
data.
tried silver foil?
I have not.
Okay. Have you tried radiographic emulsions?
Yes, I have in terms of photographing
Mm.
abilities. Yes, I
Mm.
have.
Yeah, on those radiographic emulsions, um, have you looked at them very closely?
I've looked at them in the sense that they do not impose a decent exposures on the film. So let me step back a bit. The radiographic film I use, it's produced by Fuji. It has an ISO of 400. It's
Yeah.
monochromatic, responds to blue intensifying screens. When I present that directly in the presence of the rays, maybe half a meter in front of the tube, the film is not exposed as I would expect it to, given its intensity. It's only with the assistance of an intensifying screen that I'm able to produce these images. So that brings another interesting question that with its intensity, you would expect it to be highly exposed within, a matter of
So
half a.
yeah, so what you're doing is you're using a phosphor-based polymer
Yes,
intensifier screen, and then you're placing the film next to that, and then you're doing your exposure using that as a method.
yes.
Okay, right. So, what I would suggest you do is package in paper the film and expose with a number of different, multis, crosses, or whatever in play of different materials. But then I would look at the white areas.
Okay.
Um, and look to see you should look at a presentation called A New Kind of Penetrating Radiation on the Martin Fleischmann Memorial Project's website.
Let me write that down.
Yeah, by one Shishkin.
Okay. How do you spell the last name?
Shishkin.
Okay.
Shishkin.
As it sounds. Okay.
Yeah. Um, so he was using a cavitator to make emulsion of oil and water for a client. He was a Soviet era nuclear radiation scientist expert. And when he got near to this device when it was operating, he felt really quite unpleasant. And so he started, as one would do with his expertise, adorning this cavitator with various radiographic film in different positions and planes and at different distances. And he found that these things look like little like birdies, a bit like a mushroom sliced in half, were on these emulsions. And then when he sent them off to analysis and analyze them, they found that there was pits underneath them, and the pits, it would turn out, were with a factor to the depth and the width of the atoms through which whatever this radiation passed.
Wow, that's rather interesting.
Yes. So if you had nitrogen or oxygen or aluminium, you would end up with pits that were with a constant factor the same width and with a separate constant factor the same depth in the acetate uh, relative to the atomic mass unit of the nuclei.
Okay, so it characterized, yeah, what it passes through. That's
Yeah, yeah.
interesting.
Um, so are you aware of what's called the fractal, sorry, of the toroidal moment?
I have not heard of that. No.
Okay, so you have a north and south magnetic poles. You have
Okay.
positive and negative electric charge, uh, and you have what's called a toroidal moment. And it's if you get current going in a loop and you get current going in an anti-loop, you've got a magnetic vector that way and magnetic vector that way. If they join up into a magnetic loop, Maxwell basics would tell you, if you didn't think about it too hard, that you then have a new electrical vector through the center of that magnetic ring. You don't. You have a toroidal moment.
Okay.
And a toroidal moment can be produced by a minimum of two vortex and anti-vortex. Uh, uh, and you can then fractally arrange that, and you end up with what the thing called the fractal toroidal moment. That's my name for it. They call it hypertoroidal moment in the West, and they call it supertoroidal moment in Russia, but neither of those make any sense. You've got
Yeah.
hypermarkets and supermarkets. They don't tell you anything about what they sell. You know what I mean? But Fractal
Yeah.
tells you exactly what it is. It's
Okay.
wheels within wheels within wheels. Um, and ad infinitum. And it's X, Y, Z, X, Y, Z, X, Y, Z, X, Y, Z, all the way down. Um, uh, and when you get phase relationships between these things, you can end up with a a, a non-radiating boundary outside of which there is no electromagnetic waves propagating, just scalar and vector potentials can be observed and interact with this structure.
Okay.
Um, and this was found by a guy who died in February this year called Vladimirovich Dubovic. He discovered it in doing his thesis at the nuclear research facilities in Dubna, north of Moscow, in 1965 and put it into his thesis in 1967. It wasn't verified in the West until 1997. Um, it's now the basis for next generation memory storage and telecommunications and these kind of things. However, um, the special case for that is called an anapole, which was discovered, I think, in 1954 by Yakov Zeldovich.
Okay.
And um, that is still kind of like a toroidal moment, but it's like the first pass, as it were, before it starts to become fractal. And in that case, you actually need an electric dipole oscillating uh, in a phase relationship with the oscillating poloidal magnetic fields before you get a non-radiating boundary. And this is what a stable particle like an electron in theory would have, and also like non-charge bearing particles like cold neutrinos.
Okay. I can see that.
Yeah, so the toroidal moment, it would appear, can interact with the toroidal moment of cold neutrinos.
Hmm.
And uh, the neutron and proton have their own toroidal moment. So if you have a proton by itself, or any nuclei, whatever, it has at least a proton, but anything else will still have a toroidal moment. Um, this assembles what they call the shell of the atom. So they had this theory called the shell of a model of the atom, and
Right.
the shell is constructed from condensed clusters, toroidal clusters of relic neutrinos, background neutrinos. And the overall structure of an atom in their understanding is that this material, which is I think 1.97 Kelvin, it's below 2 Kelvin, it's one fluid, superfluid condensate through the entire universe.
Right.
It gets pulled in and it answers my second question in science that I had when I was 5, which is how does an electron keep spinning around an atom?
Exactly. That's a fundamental
Yeah,
question of thought. Yeah.
yeah. And so basically, when the electrons are under energized, the constant flux of this neutral material, which actually is not at 0 Kelvin, actually has some kinetic energy,
Right.
goes through the toroidal moment of the nuclei and the atom structure. And if the electrons are slightly under-energized, an infinitesimally small amount is extracted. They go back, and because they're so similar to the condensate's kinetic temperature, they become part of the same coherent wave function almost immediately, right? Because they're basically the same anyway. There's only been if the uh, electrons are over-energized, they push their energy through this shell and give it back to the condensate. So there's this constant interplay of exchange of energy. Now, what they found is that when you properly disruptively discharge matter, you get three components. You get ions or a nuclei, which is an ion,
Right.
and electrons, and this relic neutrino, or what they call background neutrino, toroidal cluster of neutrinos, relic neutrinos. And they call that structure magnetotoro electrical radiation. And it can be neutral. And in that state, it is. Now, because it has its own toroidal moment, it can capture ions of an atom and it can capture electrons through their anapole moment. And they will orbit around this thing. And depending on the fraction of what of the other, it will produce positive or negative charge clusters, which
Okay.
they call magnetotoroelectrical clusters.
Okay.
What they found is that it's 2 to 4,000 times easier to produce clean magnetotoroelectrical radiation with hydrogen isotopes than any other element nuclei beyond lithium. So
Hmm.
obviously lithium is light, it's 6, 7 nucleons, right?
Right.
Uh, but beryllium and magnesium and aluminium, they're not too far removed from that. So you can imagine that the disruptive discharge you would have to use for those is far, far, far higher,
Exactly.
but it's still a lot less than it would be for higher elements. Okay.
Okay. Yeah, I could see that.
So they call, in my understanding, this the hidden energy within matter.
Hmm. That's
Um,
interesting. Yeah.
because it does have each of these structures that they have, I think about 0.28 of an electron volt of energy, but they describe very carefully like the volume of units that they have in there. Let me just pull up a video here and an
Okay.
image. I can just tell you roughly what that's meant to be. So if you go and look at my blog, remoteview.substack.com, and you can look, I think it's Where is the Atom Battery? And I've translated his thing.
I'll take a look at that then. Yeah.
Yeah, and he talks about, soft X-rays with energies up to 10 kiloelectron volts, constantly recorded under any rapidly occurring mechanical and electromagnetic effects on matter, and are associated with the formation and destruction of energy clusters. This is described in detail in reference 6. Energy clusters are quasi-stable formations. They are constantly present around us, but fundamental science, as a rule, does not notice these formations. Electron clusters have had many names. Tesla called them radiant energy. Wilhelm Reich called them orgone energy. Georgy Messias called them ectons. Ken Shoulders called them charge clusters. Yuji Bajatov called them erzions. I. M. Shakparanov called them Dirac monopoles. Leonid Roitzkiev called them Loschak monopoles. In everyday life, this phenomena is called static electricity.
Hmm. Okay. That's
What
an
was
interesting
Tesla
insight.
doing in the desert?
In Colorado Springs,
Yeah.
well, he was pioneering some of this research, indeed. I mean, even with
What
this
was he
too,
focused on?
through the transmission of electrical power via
Uh,
his
he had a
magnet.
very large copper ball, and he would put it up as high as he could into the
Right.
sky
The
to
capacity mass.
accumulate static electricity. Static electricity. If you, I've done this. I've done this with a room of 500 PhDs. You ask them what
Right.
static electricity is, they haven't got a freaking clue.
Right.
They start describing how you observe static electricity manifesting. The best answer you might get is an imbalance of charge from here to here. But the actual
Well,
thing,
that's always
you
And it's
know.
always referenced to what is it, using a piece of amber and
Yeah,
a
well,
rubber.
the Greek for amber is electron.
Right. That's what derivation.
That's why that's there.
Yep.
Yeah, so rub a bit of amber. Yeah, so or cat's hair. Um, so the point being is that static electricity, as far as I can work out, is a charge cluster, and it's this cluster of Reliant neutrinos onto which you can have positive or negative accumulations of electrons or ions. And I'll just see if they've got the. Is it in this one? I don't know whether it is. Oh yeah. So they calculate the explosion from a charge cluster. So they've been working on this for 9 years at the point that a lot of these papers were written. Um, okay. Another one called Suggested Model for the Cold Transformation of Elements. So they say a magnetotoroelectrical cluster, or radiation rather, contains 6.93 times 10 to the power 20 elementary inductor capacitor dipoles. In other words, background cold neutrino quanta.
Okay.
Uh, it consists of 7.71 times 10 to the power 10 electronic vortices.
Okay.
Each electronic vortice contains 0.89 times 10 to the power 10 elementary LC dipoles. So you combine those two together and you get the 6.93 times 10 to the power 20 elementary LC dipoles. The mass M of an M-Tech is about 1.0235 times 10 to the power minus 40 kilograms.
Hmm. Okay.
Right. But if you take that and you times it by uh, uh, you know, E equals mc squared, it's still going to be quite a bit of energy.
Well, certainly. I mean, given those figures, yeah.
So this is the hidden engine within matter, and he's calling these etheric matter this. And I firmly am subscribed to that based on my understanding experiment. Now, um, when it comes to the pyramid, I believe it's an etheric matter accumulator and condenser. And in fact, all matter effectively has to come from wound light, and some of the weakest wound light is this relic neutrinos. It's mass. It actually has mass.
Right.
um, and so it's basically what you might call the prima materia.
Okay.
Uh, and you can condense it further if you can convert it through unification of the forces into just raw energy and then crystallize it out basically into other wound light, if you can imagine that.
Okay.
Uh, so the Earth is, in my understanding, doing this. It was, according to Constant and Mail, the Earth's day was 19.2 hours 900 million years ago. It was 21 hours 200 million years ago, and today it's 24 hours and getting longer because you have the magneto-hydrodynamic structures going on with the Coriolis forces and the plasma, which is in metal anyway, but it's a solid plasma, but in liquid metal and with the magnetic and blah 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 and the shear forces going on, you end up with the structures that are able to produce toroidal moments, which are able to condense this matter. Now, what you get when you have a fractal toroidal moment, which is something like this is a wound version of what nature does beautifully. So
Okay.
this is a coil within a coil within a coil within a coil, right?
Okay. I
When
can
you
see that.
get that, you get a phase singularity at the center, right? But it doesn't really work as well as when it's done with plasma. Um,
Right. Well, it's a
you get a
different.
phase singularity, and the phase singularity has the Aharonov bomb effect, and also there's a phase singularity in the center of these, which has the Aharonov bomb effect, and that
Okay.
can cohere by first forming Cooper pairs and then and producing condensate of electrons that come to a magnetic phase singularity, where the magnetic strength gets stronger and stronger and stronger. And you end up with what's called a vacuum current, and it can do things by like assemble matter and cause matter to fall apart. There's a guy called David Freiberger. You can go and look at all these papers.
Burger sounds familiar. Yeah.
Yeah,
I
so
mean,
he worked at Slack. I think he still does. Probably nearer to you than me. And he did a treatment very similar to a guy called Nevesky, who did a treatment in 1988 in Russia before this was in the West.
Okay.
Extension of Maxwell equations. They found it has a pointing vector that's closed in on itself if you have a wheel within a wheel and a wheel. And if you have another order above that, you have a pointing vector that's 90 degrees to that. And you end up with what they call in Russia an electromagnetic phantom, where you can put power in and it doesn't dissipate, it's closed.
Okay,
Um,
I see.
and you can
Yeah.
just build up and build up and build up. Freiberger describes this as having a vacuum current, and it when you get the what he calls the diality angle over a certain critical threshold, it can cause baryons, that's protons and neutrons, to lose their reference to the Dirac sea and fall apart.
Really? Okay, that's actually
So that's
unusual.
disassembling matter entirely. The
Exactly.
the vacuum current itself, according to the 1995 paper of Zverblis, who worked with Nevesky on trying to understand what he saw in a Moscow basement in 1988 with this vacuum current, this electromagnetic phantom, calculates that can capture photons released from vacuum fluctuations, you know,
Hmm.
production and annihilation. If it
Okay.
can do that, then there's a reasonable assumption that it can reach energy density such that it exceeds the Schwinger limit and it can trap all light and mass.
Hmm.
So
Okay.
you
Yeah.
effectively create little black holes. Now, why am I telling you all this?
Well, I
Um,
can see how it partially relates, yeah, to the phenomenon of the tube, especially its emissions and how it behaves with matter.
yes, and with the reservations that I've had in the early part of this conversation, I have to say, potentially, congratulations, because you may have developed yet another, but not as easy as the ultra experiment, the ultrasound experiments, which you can do for 35 or 40 pounds, but certainly something that's more visceral and interactive, um, because on your structure, you have this very perfect magneto-hydrodynamic structure. And before I close out, I want to just show you an image, and if I can share it with you, because I
Okay.
think you should see this first. Uh, it's just really annoying. I just hope I can get those videos. Otherwise, I've got to just go back and do another session, and I'm running out of time because I'm meant to be going to Canada on Sunday.
Oh, really?
Yeah. Um, right. What am I looking for? I'm looking for Photoshop here. So I'm going to, with the provisos that I've talked to you about we need to do some more evaluation.
Correct.
I am going to, um, why is that not opening? Okay. What? That's weird. I'm not having a lot of luck here. Uh,
Doesn't want to cooperate.
okay, here we go. Right. This is a map, and I need to share it. I need to get my mouse working. Where's my mouse? Okay, Bluetooth on. Okay, firstly, I'm going to show you the electrode itself,
Okay.
which you've seen. I've got it on the microscope stubby at the moment. Right.
Yes. Like the pitting surface in the center, that's
Yeah.
where spiral direction is.
Uh, Let me see if I can get a light on this. Okay. And that's a lot of light. Right. Can you see?
Oh, I could see the cavities.
Yeah.
Okay.
Right. So I'm not interested in the ones in the dead center, which I
Right.
suspect are from your spot welding process.
Right. That's
I'm interested in the two that look like the eyes on the face there.
oh, okay, I see. Yeah, because those are definitely off-centered.
Yeah. and kill my ridiculously bright light there. When I saw that, I got rather excited.
Yeah, I don't recall seeing those. I mean,
Yeah, well,
then again,
you
after
you also
building
have to
some,
have the eyes to see, and I'm going to be
definitely.
giving you the eyes to see now.
Oh yes. Well, I mean, after building, more than 50 individual tubes, each electrode looks relatively the same, more or less.
Yeah, I know. But from me, um, I'm going to show you something first, so that you know where I'm coming from. What should we do? No. Okay, this'll have what I want. He says, but I'm not finding it. No, no, this is not going to do it. Bear with me just a second.
Oh, no problem.
Uh, it's taking its time. Okay, is it loaded in? Okay. Yes, it has. Okay, this will do. Right.
It was able to load.
I've got something which I can show you what I'm going to be referring to here.
Okay.
Here. Screens. Um, Screen two will be okay. Desktop two. There we go. Share. Okay, it's now asking me to open system settings to allow me to do this. Yeah, problem with a new computer. Now it's asking me to quit and reopen Zoom. I'm not
That's
sure I
great.
want to do that, but yeah, I'm not sure I want to do that. Oh God, this is not very helpful, is it? Later. Let's see if it'll let me do it anyway. Desktop two.
Okay, there we go. I can see.
Right, okay. Yeah. So can you see this little thing down here?
Yes, I can.
Right. That is, and you will see the same shape as what you have on your
Okay.
sample. Um, these are, well, here's your toroidal moment structure. So magnetic loop, sorry, current loop, magnetic moment.
Okay.
Take at least two of these and arrange them in a ring. So you get a ring of magnetic moments that gets a toroidal moment, and then you can just stack them so that this is a wheel made of magnetic moments, and then you rotate that and rotate it that way, and that's a wheel within a wheel, and this is a wheel within a wheel within a wheel, right?
Okay, I can see it. Yeah.
Okay. And through studying of a John Hutchison sample here, I have various quantizations here, and I derived this. This is the same structure as this. This is looking at the apple core from the side. This is looking from top down. And then
Okay.
you take that structure and rotate it, and you've got 48 divisions there. And so I derived this, which is your wheel within a wheel within a wheel structure. And each of these is a perfectly conducting current loop, if you can imagine it.
Okay.
Um, uh, and it's fractal all the way down. This is in Science 2011. This is in copper oxide. Uh, uh, copper, 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 oxygen atom, current loop, current counter loop, toroidal moment coming out the front there.
Okay. Yeah. See. Yeah.
This is in copper oxide in one of our experiments, and this is on tungsten. And it
Interesting.
can tear matter apart, okay? But you can see the overall shape. So I've got the same kind of shape here. So this is tungsten.
Okay.
This is the yin yang. This is exactly and precisely the shape of Wardenclyffe's tower, right?
Right.
This is in an ultrasound experiment with lighter elements being made here by extracting oxygen from the aluminium and firing
Okay.
it around here and producing calcium and silver and stuff here. Now, in your electrode, you have silver, you even have tin.
Okay. Yes.
You also have quite a lot of tungsten, which, we need to get to the bottom where that's coming from.
Right. As we
This is
discussed.
boron here. These are boron crystals in the
Okay.
center, inside the Vesica Pisces, inside the golden ratio line. That's where this particular shape forms. And over here, I can zoom in so you can see it a
Oh,
little
there
bit.
we go. Yeah, that helps.
Right. And it has an event horizon here, has several event horizons. So you can see the Vesica Pisces here and the crystals there. This produces and is exactly and precisely the same as a bar spiral galaxy.
Okay.
This is the yin force. So it's actually consuming the matter in here and making heavier elements. But there's a phallico-soliton that loops between these two.
Okay, I see what you mean. Right.
Okay. Um, and you can get the similar structures from Winston Bostick's work on plasmoids. You know, you can abbreviate that to plasmatoroids. This is
Okay.
Vladimirovich Dubovic, and he's talking about how the structure will suck chi out of you
Hmm.
or through you. So
Okay.
this is one risk you need to be aware of,
Right.
that in the direction there's these two triangular things with a little white bloom above, and I'll characterize this hopefully, and I'll get my videos hopefully by the end of Friday,
Okay.
what come hell or high water. And um, through the back end, you can see it has a flow. So this is flowing in here. So there's like material coming in, and this will be sucking chi from the environment. So
Okay.
there will be an area around your uh, sample that may be not a very good place to be to get too close to,
Okay, I see what you mean.
right?
Yeah.
Now, um, let's see what other examples I've got here. So what it does is it creates a topological monopole in here at the phase singularity. Okay. And it's the same shape as this. So you've got the two bits that point in, and then you've got this white plume up here. So that's what you're seeing on your structure.
Okay.
And they have various quantizations, but they must be minimally two. So yours effectively would be a two with a kind of vortex going on. And it will be producing a beam from one side. So here, this is it in 3D. So this is a 4-4-4 structure, making four. So the swastika is the first time the technology becomes under control.
Right.
Um, this is on Winston Bostick's work here with Nardi in 1980, and you can see they have toroids that have toroids made of toroids.
Right. That looks very similar. Okay.
Yeah. Here, these are collapsed wave functions in our experiments. So we got 36 here. This would be 48. There's a number here.
Okay.
These are when these structures collide with fused quartz. So here we've got a 6-order structure. Here is a swastic structure. Here's a
Oh, yeah.
multi-ordered structured here. Okay. So these are various clusters of these things.
Okay.
Um, Here you can see it in a wind hex. This is in the wind hex pattern. This is how a tornado works. And it's a normal tornado will like typically only have two, so it produces a vortex coming in here. And this is dark matter interacting with the electrons and the matter in here, such that there's a frictionless zone here, and there's an event horizon. Uh,
Okay.
so there's several things that I'd like you to test, and we can go into those at a different time. But here's a cavitation one, and this is a cavitation in Roy Schinamarza's steel vibrator plate. And on each side of the vortex and the anti-vortex, the vortices have cut triangular holes.
Yeah, no, that really is interesting.
And that's because it has substructures in there.
Right.
And the matter is moved between those substructures. So
Does it
if we go back
does
to
this
the
occur on other parts of that same sample, or is it mainly in that section?
oh, this is just one example, but like
Okay.
if I go to the plasma reactor, where is it? Up here. Where are we? Here. We managed to make this hemispherical section of copper disappear. But if you look under the SEM here at the boundary, these self-similar structures, because they have the toroidal moment, they get kind of stuck on the outside, like a onion with cloves in it, if you imagine.
Okay. Right. Right.
And you have a two-order structure with a vortex, a three-order structure. This is a three-order structure, but it creates a vortex in the middle. This has still got a vortex, but it's like a very focused beam. So when you get four with your square hole with a square hole in the middle, which is always quite interesting, even better than a triangular one. But these beams don't go out. And when you get five, and it's very precisely, I worked out why. It's because when you overall rotate the three-dimensional structure, it has a disruption area down here, which is the notch in the Sothic triangle. Okay,
Okay.
this is always associated with the ankh in Egyptian engravings, and this is the Sothic triangle angle is the same angle as the building of the Wardenclyffe Tower. Okay, for very precise reasons. Um, and so it extracts energy from here. This zone here, this zone here is the zone in this experiment where it's converted this tungsten into strontium, and it's disassembling it. It's like depressurizing it so much so that or over exciting it rather so much so that the matter is falling apart.
Okay.
It can't maintain its normal structure, and then it pulls it in here. And these are all of the elements in stellar synthesis from tungsten. And this experiment was seconds long. It works very quickly.
Okay.
Um, and so um, the reason I'm showing you this is like, okay, so this is a sample where we had a piece of brass here on top of a piece of iron. This is collect to produce our ball lightning. And you can see here, this is exactly and precisely the structure of if I press play here, the sacred geometry there, the way it's deposited the copper. It's also exactly the same as the Great Pyramid, all of
Okay.
the positionings. And when you look at the top side here and I play this, you can see the geometry here. This is the disruption zone here where this triangle is, and it's offset just as the subterranean chamber is on the Great Pyramid.
That
Okay.
is true. Yeah.
Okay. And that is where it's extracting matter and it comes up. It has to come up this descending passage, this what they call the well, because it has to be inside the event horizons of these two structures. Okay.
Okay.
Um, and there's a wormhole that goes here. This copper is not penetrated, but it is consumed on the backside. You can see here it's from this side and it's consuming the material. It's punching it through a wormhole. Here, when you look at under the SEM, there's nothing there, and there's an event horizon here on this inner side, and then it punches through, and it's already coming out the wormhole, and it splats it down, and that's what you're seeing here with the copper splatted down on here.
Okay.
Okay, and this is all the magneto-hydrodynamics. And when you look at the structure here under the microscope, this is all just kind of brushed brass. You see this. It's a hexagonal array of cones, which is
Hmm.
Maxwell's model of the physical vacuum. You see this also on aluminium in Hutchison effect. Different. These are two different Hutchison effects with the regularly spaced stuff. Now, this is all over your sample, these regularly spaced structures.
Okay.
Okay. And so this is on the brass sample from the test we did in brass, and it's exactly the same physical scale as these on the. This is from 1980
Okay. Yeah.
from the Hutchison effect, and this is from 2022,
Okay.
and it's all part of this. Here we go in a cavitation experiment. That is the 3D geometry, and you can start to see it looks a bit like the Wardenclyffe Tower.
Right.
Um, the distance between the top of the apple and the center here is x, and between this line and the point of base of the point of destruction here is the golden ratio, and that is the same for every fractal level.
Okay. I could see
It's
that. Yeah.
why the universe is structured as it is. So if I which one do I play? It's the next one. What I'm saying is it isn't hard for me to see stuff because I've seen so much of it.
Yeah, and you could easily recognize where it's going to be
Yeah.
similar.
So what's happened here is the inner vortices here of the magneto-hydrodynamic structure have actually come out and they're here.
Okay.
And this one has broke down, and there's a wheel here that was inside here and another sub wheel here. So
Oh,
this
okay.
is the n level tour. These are the n-1 level tours, and these are the n-2 level tour. Wheel within wheel within wheel.
Right. Okay.
Okay.
It's almost like puzzle pieces. Yeah, especially the N2 section. It fits right in.
And here is a vortex and an anti-vortex. This is a yin, this is a yang, this is a yin with a yang and a yin, and this is a yang with a yang and a yin, yin and a yang.
Okay.
And you know, oh, I haven't got it here. Maybe I've got it here. I got it here. Okay. I can show you here. This is talking about. Can you see this?
Yeah, I could see it.
This is from Physical Review B, American Physical Society Condensed Matter. This is from 2014, peer-reviewed journal. This is the axial hypertoroidal moment, and when you get the field structure going one way, you get an apple shape this way, and when you get it going the other way, you get it that way. So this is from the same experiment. I showed you the wheel within a wheel within a wheel. This is overall apple and the anti-apple here. And
yeah,
so
you can
we
see
know
it.
that it's a toroidal moment structure in there, fractal toroidal moment. We know for certain. This is what peer-reviewed says it should be on the nanoscale, but we're producing these things at, well, that's 10 microns at scale. These are absolute phenomenal quantum objects.
Right.
And it's all scale invariant. So here's
Okay.
a couple of ways you can look at it. These are two that got caught into each other. This one here is breaking up and there's two subwheels are coming out. This one is emitting stellar synthesis material from the phase singularity inside. This is all copper oxide here. This is other elements that it synthesizes on its boundary layer, and this is elements synthesized here. This material is blowing out from inside this structure.
Okay, you can see, yeah, the projection point.
It's just broken out. And this is all the elements you typically get in stellar synthesis. Here, you can see this one's completely broken up. And as the substructures have been falling apart, it's actually created a braided structure. And this has things like titanium in it, which is, nowhere near in there, but titanium is carbon and oxygen fused. Here, the vortex is so strong, it tears copper out of the copper pipe. And that's going into this one, and the other one in here is spewing out the stellar synthesis material. So the typical structures are 20 microns across here on this level, which is the inside of the apple. Okay, this is the apple shape. Okay, now I haven't scaled this, or all I've done is I've rotated this same symbol with the same 20 micron scale on the same microscope. Here is two insides. You can see what I call the fat Oreos.
Right.
You can see the fat Oreo here, but this one has peeled away because they tried to fold on themselves. So here, it's actually still got the hole where the center of the vortex goes through.
Okay.
Right?
Yeah, you can see that.
And so here, this is an element that's been synthesized inside. It's come out as coherent matter, and as it's de come out of its coherent matter state, it's just bloomed as new element crystals. Here you can
Compared to the
see,
other situation where it was merely released,
yeah,
it didn't really condense.
yeah,
Okay.
it's come out of the core within a core. So
Right.
it hasn't come out. This is the substructure. So this is 5 microns, and if you do the mass, these are all 5 microns here,
Okay.
right? So, and it depends how much it's spun up because it might have consumed more matter. It might have been resonant for longer. So if it
Okay.
keeps chucking stuff in there, it'll make whatever element you want. So these ones, when they're big, you're getting this typical stellar synthesis, but you've got to think that the substructures are doing the same as well. So this is mostly carbon that comes out at this level when it's not spun up so much. But whatever this is, I think actually the SEM wasn't doing EDS at the time. This one, you can see the tornado coming out the bottom has touched down on the copper here, and it's stripped some of the copper up, and it's also pulled it down and then forced it to crash into the surface. So it's sucking up, but it's pulling itself down on the surface. So it
Okay.
touched down, and then the whole structure collapsed. This one broke, and a tornadic, uh, counterflow broke out. So the vortices that's going on in there at the core then broke out, and it layered the tornadic material of synthesized material out. Right. Anyway, why am I showing you all this?
Well, I could see how it's relating to this. Yeah.
Yeah, I'm showing you this because of this. This, my friend, is your electrode.
Okay.
And when I look at that, I see exactly and precisely this structure. Now, my problem is
Mhm.
that these are similar to spot welding.
Okay.
And the problem is with that is that spot welding was what Randall Mills used to demonstrate brilliant light power energy when he did spot welding, right? And spot
Right.
welding will produce eddy currents, and eddy currents are related to magneto-hydrodynamics.
Okay. Yeah,
So
that's
this
true.
is why we must find a way of getting an electrode, running it for long enough in your device in such a way that it's not mounted with spot weldings on the center.
Now that I think of it, the friend of mine, the colleague who does the machining of the electrodes, it may be possible to produce one that has a cup of a stem where spot welding would not have to be needed. It would just be a very special construction, but I think I could see to that, see to its
Okay,
construction.
because I need to separate this from potentially an artifact of the spot welding. But
Right.
regardless of this situation that we are faced with, here is the sacred geometry overlaid.
Okay. I can see that.
So, I mean, I could see this with my naked eye. You can
Right.
see the vectors of the flow patterns. So, like, uh, this is flowing around this way, this is flowing around this way, or whatever. I might have got this upside down. The thing is, these things are slightly mirrored. So
The
I
fact
could
that,
take it. So it's either one or the other way up. But because you've got the flow in here, the flow in here, the flow in here, and then it's kind of goes up to this point here. And you can see there's nothing outside here. That's over there. This is all inside here. Now, typically, as I showed you on the brass over here, where is it? The brass one here. I got it in this one. Or was it in the other one? You see how here it's swept around on this side, not this side, because it's pulling from here and it's putting down here.
yeah, it's only on
It's
one side.
taking it's taking from this side in the pyramid and it's dumping into the sarcophagus over here,
Okay.
right?
Right.
Okay. So if I go back here, it's taking from this side and putting down here. So I might have this 108. It should be flipped the other way. I haven't decided yet which way this should be up. In when I'm looking at the flow patterns here, I'm thinking it should be the other way. But either way, this part is symmetrical. And why is this interesting? It's because you have a different density and arrangement of these fibers here around here. And these, amazingly, are like strips of iron.
Yeah, no, that is interesting. I mean, of course, I would have never been able to see it in
No,
this
you
detail.
can't. Well, you can under the microscope just about see the marks, but unless you know what you're looking at, you don't know what it is. And I've seen
Exactly.
these kind of marks on different systems
Okay.
coming from these monopole-like structures. It produces what's called a topological monopole. Now, look at this over here. There's none of this stuff outside of this boundary layer. And that boundary layer very precisely is an event horizon in these structures. And then you've got nothing outside here.
Circular. Yeah. Well, then also just its path that it curves itself to this shape.
Yes. Now, if I undo this structure here, I'm going to take out the, and I'm going to have to go in a minute because I'm meant to be taking my family to dinner.
Okay.
Here is the fractal toroid. This is the substructure within this overall structure.
Okay.
And when you look at this on both sides, all of the synthesized material are in this side. In fact, I'm pretty sure it's the wrong way round now because that is where we saw the boron crystals before.
Okay.
So you remember that thing that I showed you earlier?
Right.
Where is it? This one.
Those.
It's in that image, but so it's down the bottom. Is it down the bottom? Ah, la, 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 la. Just trying to find the higher res one. Yeah, it's here.
Okay.
So you can see
Yeah.
this part. So what you have is within this right. Within this white line, you have your subtor structure. So the subtor structure is sitting inside this white line, and there's the boron crystal. So if you can do the flip in your head, that's where that bit is.
Okay. No, I could see that now. Yeah.
Yeah. So the other material over here would be down this side here. And the interesting thing is, this is where all of the damage is in these 2 points.
That's true.
So if I do there, you can see it's all within inside the tor. All of
Right.
this material here is within the tor, and this is the center of the tor. There.
Yeah, it is
So
isolated.
I need to combine the oh, and by the way, this is the non-radiating boundary. So I think why your system is working is because the charge is getting bounded by the silicon dioxide because there'll be charge on the boundary. It charges the silicon dioxide, and that causes the structure to be inside that because it's charged on the outside, and the glass gets charged and it gets confined there. So
That's
you,
exactly what I've hypothesized before, because it's also evident by the way the plasma interplays with the beam formation and just the overall warm-up process that the beam itself will directly confine itself to 90 degrees perpendicular to the surface in a similar arrangement and project itself outwards, but it is confined more or less, and that's how I was able to obtain that specific tube geometry to maximize that level of confinement. So yeah, no, this is definitely
now what I
area.
can tell you is in here and only in this area do you have all the stellar synthesis.
Okay.
You've got potassium, calcium, sulfur, uh, chlorine, magnesium, silicon. Of course, there's maybe those in the aluminium.
Okay.
You've got nickel, you've got copper. Of course, you've got copper in this system, and you've also got copper in the nickel in the system. This is why we need to look at having very pure aluminium
Right.
and very precise manufacturing, and then getting this spot welding out of play.
Definitely. Yeah, to
Uh,
eliminate any possible
but
chance.
whatever, whether this occurred with the spot welding or it occurred because of your process, which I suspect it did because of the synthesis of new elements in here, which are the same elements that are being synthesized, spewing out of these structures in cavitation.
I mean,
right?
as far as because to be honest, when I sent that electrode, I did not see those two independent spots. They did not pop out in my mind, but knowingly,
You don't have the
assembling,
eyes for it. You know, we are built in the image of this technology. Vortex,
okay,
anti-vortex, Sothic triangle. This is the point of destruction. Same with
okay,
our two tits and our belly. The whole physiology of the human form is
yeah,
an image of the technology that runs the universe.
right, likewise, yeah.
And
And
so here is the real kicker. Um, when you have four, five, or six, the not the, this disruption beam goes into the apple of the one at the fractal level rotated orthogonally, right?
okay,
When you have six, it's sorry, it goes into the non-radiating boundary. When you have five and six, it's complete, it's starting to be in the apple and then completely contained within the apple. So six gives you the flower of life and it's totally stable. But when you have three and two, that's when you get those vortices, not a square. The square one, which is the swastic,
yeah,
doesn't have a vortex.
okay,
And this is why you get a two-arm spiral galaxy, a three-arm spiral galaxy. But as you go beyond that, it starts to become a ring galaxy. Okay.
okay, I can see that, yeah,
Here is what you have on your structure, a minimum two. And what happens is you have a beam of etheric matter rays, which is ejected through the top. So it can't get go, it's extracted here and it fires out in a beam in front.
okay,
Okay.
right,
Or whatever. It's orthogonal. So this is
right,
happening on the pyramid. It's extracting and then it produces a. Now some of it goes round in a loop. Now can I show you that in some cavity structures? Cavitation. I can with. Okay, that's going to be useful if I can go ultra. Here we go. I can show you it in bubble structures in water. Um, Here. Look there. Same thing.
oh yeah, it
This is a
is,
wheel. This makes a wheel, and this makes a wheel. So this is a wheel within a wheel within a wheel. Okay.
okay,
Over here, you can see what it does. There's a beam coming out and another beam going the other way. And this is the center of the fractal toroidal structure here, and this is the center of the fractal toroidal structure here. Now,
yeah,
you've identified yourself that the aluminium stops it, and surely it does to a degree. Why? Because of the high conductivity of the metal. It has a lot of free electrons, and the free electrons bind onto the relic neutrino cluster, condensate, and they make it into a white mode, and so it can't penetrate the metal that way so much. But one of your beams will be shooting out.
okay,
That is your source, in my view, of your etheric matter rays, your radiant energy, your charge clusters.
okay, I
And they
can
are
see that,
neutral because you're using aluminium.
okay,
And so you've basically got a black hole, what an actual black hole is, in my opinion, not what they say it is, and what actually black holes are.
okay, yeah, the functioning process, okay,
And it's shooting out this energy from its pole.
okay, so yeah, it's a specific spot, you're saying, where
Yes.
it's
Yes.
originating from. That does corroborate the observations I've made when it is on the pump, on the vacuum pump itself, that the beam, as it slowly starts to form, as the vacuum increases, the degree of vacuum, that beam will start to coalesce to a very specific spot, or near the pitting areas where the spot welding has left its remnants, and it will stay there even while the tube is in operation. I faintly observed it that it is a very narrow beam, a needle point, if you will, and it does seem to corroborate with, I mean, what you're saying here, especially with these pits.
What
So
I'm saying
that's
to
very
you,
interesting.
what I'm saying to you
Yeah,
is between us, we have proven potentially, if we can verify this with some more experiments, with some null tests and the modified electrode to get rid of some of the questions that are arising from this, we
right.
proved that Nikola Tesla was transmuting elements in the late 1880s, 90s.
Oh, that would have profound implications today's society for that to be grasped. So yeah, I
We've
mean, this
also
is
proven that because this technology typically only produces stable elements. If you wind this thing up, it'll make any element in the periodic table, even
I would
things that don't
imagine. Yeah.
exist in our near universe, right? This was found by Etheric at Proton 21 Labs, right?
Okay.
And he was creating one of these intense fractal structures and firing it basically through a 300 joule dielectric barrier discharge into a metal target.
Okay.
And they did something like 5,000 consecutive, or I think even as many as 10,000 consecutive experiments. And from the first to the last, every metal target they used produced pretty much every element in the periodic table.
Wow.
Every
That's
time sequentially for 10,000 hits,
yeah.
right?
I mean, that's more than adequate proof.
But that's a pulse disrupted discharge producing this material.
Right.
Yours, like many of the systems, like the cavitation one that I've shown you, is a resonance system. And what you're doing is you're building these structures by producing a few of them, they're clustering, and then you keep feeding it. You feed the beast until it becomes a very powerful little machine. And then in
Okay.
some of the substructures, like in this overall area here, you're not seeing necessarily any transmutation, but it's within the substructures that you get to see the wheel within wheel within a wheel that you start to see matter being either torn apart or assembled.
Interesting.
And so you can take radioactive material and you can make it non-radioactive.
That was a possible experiment that I had conceived of. I haven't been able to employ it just yet, but the
This is
beam
my next thing
itself
that you
is
need to test. You need a
one
source, you
one
need a beta source because this is neutrino radiation, neutrino cluster radiation.
right,
So you need
right.
a, ideally, if you can find someone who can give it to you, cobalt 60
Yeah.
source.
I actually do have a surplus of small experimental radioactive sources from
Great.
cesium to
Get
polonium.
your
Yeah.
cobalt 60 because it's a beta
Okay.
isotope. Cesium-137 would
Right.
be fine, but the half-life of cobalt 60 is like 3.6 years or something, which is 10 times less than well, not 10, but
Cesium
nearly
is
an
30.
order of magnitude less than cesium. So that would
Right.
be my preferred thing to use.
Okay.
And I'm just shutting down here because I'm in trouble now.
Okay.
But this is very, very important because the significance of what we're doing here is potentially I'm going to be directing people with caution because a lot of scientists I've been talking about the ultra experiment, which is a 3-year-old can learn to do it and conduct it successfully in 7 minutes. It produces the yin yang magneto-hydrodynamic fractal toroidal generating structures within a few fractions of a second, and it starts synthesizing new elements almost immediately. But because it's so ridiculously simple, it's literally Galileo saying, "Look through the telescope, please,"
Right.
uh, and you can see X, Y, and Z. You can't write a budget proposal on that. You can't fund a university department on it, and it doesn't look so pretty. You've got to pour water and press a button and fold aluminium foil, right? Your experiment looks pretty, and overall, it's a much more expensive endeavor. But it's kind of the sort of thing that would look in place in a lab. I think I mean, this guy, he was able to do these things, creating this is from pure lead wire. And from
Okay.
the lead sphere here, from this azimuth, it's ejecting carbon.
Oh, okay. I can see. Yeah.
And there's no carbon in the system in many of his experiments. So
Interesting.
carbon's 12 nucleons, lead's 204, 6, 7, 8, right?
Yeah, for
So
that to
you
be
can make a lot of
manifest.
12 from 204,
Right.
6, 7, and
That's
8.
what.
And it's
Hmm.
coming from the inside. It's born inside the center. In the patent by SV Adamenko, it says dark matter, and there's a unification of the forces basically in these hollow spheres, which typically are iron, but like if you start with lead, you're going to get a lot of lead. This experiment here
Yeah.
uses mains voltage, one millimeter lead wire in an electrolyte, and it's 3 millisecond length pulses. That's it. Dun 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 done.
It's simplistic. Yeah, in
So
operation.
simplistic, but it's too simplistic that most labs won't bother it because you can't write a grant proposal and look like you've got
Exactly.
patented IP to look at.
No,
Now,
similar colleagues are in the same circumstance that it's too simple. It's not complex enough to grant or issue a grant.
what you've got actually, I think, is beautiful because it shows it's a source of this radiation. Everyone's asking for a source of this radiation because I haven't wanted to do various experiments. By the way, it can give you cancer. So
Yeah.
please be aware.
Oh, I exercise precaution. Great
Right. The,
precaution.
the reason it can give you cancer is because it can take potassium 40 and it can take carbon 14, potassium 40 in your salt in your blood, and carbon
Right.
14 in your sugar molecules, one in every trillion atom in your DNA, sugar molecules that bind your DNA together are uh, carbon 14. And it will cause those beta isotopes to decay. And if you go and look at Shishkin's, a new form of penetrating radiation, it can carry other atoms with it. And when the thing dishevels and blows up, it shoots these out with enough kinetic energy that is equivalent of Gray's damage that can cause red blood cells to be destroyed and white blood cells to have the genetic damage.
Okay.
Right. So
Yeah.
don't be so sure that this is safe to play with. It's
Oh,
fun.
I'm not making any claims. I always exercise the greatest of precaution as far as, I mean, my research goes, because it is, I would say, limited, of course, to other research facilities, that I have not yet observed any mutations or biological adversities
No, no,
in
it's
certain
clean. You're producing predominantly clean etheric matter streams.
so
So
far, as yeah, as
yeah.
we get.
Now I have another concern. Of course, you're not firing into a metal
Right.
and it bouncing off like you
Okay.
normally get with braking radiation producing X-rays or gamma rays
Yes.
for a target. But you are my question was, is the iron, nickel, and copper that's in these areas of synthesis in this sample, are they
Mhm.
being produced by the process? And if they are, then over time, you might get heavier and heavier elements, and that might produce a risk ultimately of higher energy photons coming out of the system. So,
Exactly.
which is why you need to do extremely long tests and monitor it over time. But Griffin, hats off to you, mate, for actually trying to do something, looking back in the literature and doing the experiments. Freaking brilliant, mate. Absolutely brilliant. And the way you're conducting yourself, there's a lot of people that could learn a lot from you in your approach to this. But I'm going to be directing people to buy the hell out of these devices on
Oh,
speculation that this isn't caused by the spot welding. So
yeah, and
expect a
that's
lot
what.
of orders to come your way.
Oh well, hopefully I could keep up with those. I mean, my assistant that used to be helping me with the glass blowing, he no longer is able to be of service, so it's merely just me, one man operation, and it's rather tedious, but I mean, I enjoy doing it.
I think you're going to find that you'll be able to hire some people because this is the kind of test that's simple enough that with you're probably going to want to ship the suitable Romikoff coil or whatever it is you're going to be using, whatever it is you're using for stimulating the device.
I am working on a power supply with another colleague as well.
Are you going to
It's
do solid state or
we're still debating. So I've essentially been replicating Tesla oscillators that he used in the 1890s for this, the oil box oscillator as well as the Mercury commutator control switch. I've had success with it, but it's not exactly commercially viable just yet.
then so okay, so you're going to need something because like David has all this stuff and he can just take the tube and run with it, but not
Right, he
everyone is
does.
in. Yeah, not everyone is in that position. So
Right,
there's you're going to have a market now. Like if you can produce the real time pseudo X-rays, you're going to have the market for the whole system.
right,
For the actual real time X-rays, even if people are just dropping in on a you know a a grabbing arm so that they're not exposing themselves to the rays, and they're putting other objects in there like solid objects or whatever, or they're putting nematode worms in there to see if there's long-term radiation issues, whatever.
exactly.
There's going to be a whole huge market for this, um
Definitely.
to study this. So yeah, I think with a little bit of effort, by the early part of next year, we can confirm that this is doing the job.
Okay.
If it is, it's totally profound because it's very difficult if it's cleanly produced to have the criticisms that they like to make with the cavitation. Oh, it's just accumulation of it does accumulate stuff. Yes, it grabs iron out of anywhere and pulls it into the magnetic core, but it makes these iron-rich crenellated microspheres which are hollow
Right.
and they look like brains and they look perfectly like smooth, but they don't rust as well. They're FeO2. They're like a weird oxidation state that was only produced at 1700 degrees at some ridiculous number of gigapascals in a diamond anvil in 2017 to find this new phase of matter. It seems to be the same phase and it just doesn't rust. But it anyway,
Okay.
these things will eventually be produced, I imagine, in these systems of yours. But the fact that you're getting the same stellar synthesis in those zones with all of those typical elements that you get out of stellar synthesis, I believe this is the way black holes work, stars work. Um, it's totally profound. It is the process for me that all then occurs, and it is based on the natural phenomenon of ball lightning.
And I'm glad to have your input on this. I mean, it really does introduce some new topics and opens the door for, new research to occur. So I keenly look forward to what the future holds in this regard.
What are you doing? I know in the video from 2023 it says you're going to college. What is your plan?
I'm still in college right now.
Right.
I'll be finishing in the next year, and
Okay.
afterwards I'll be looking for, I wouldn't say a, long-term form of employment, but definitely something with the local electrical utility systems in terms of actual apprenticeship programs, which they do offer. I'm mainly looking into the industrial side of electricity as employment because any other forms of research related employment, they're not necessarily interested in these types of topics. And of course, to become interested in what they are interested in, I'm not exactly in favor of that.
Griffin, I
That,
think you can get a job anywhere, honestly.
yeah,
But
definitely.
if I have a chance to work with you, I'd really like to do that on a specific project next year. It might take a chunk of your time. When are you finishing your studies?
I would say let's say the fall of 2026, most likely,
Okay.
or
When are
around
your
that time.
holidays?
Oh, can
When
you
are your
repeat that?
holidays?
My holidays, let's see. In terms of this one, it will be between the 14th and the 1st, no, and the 5th of January. I have a break during that period, but afterwards it's merely just school. I don't have any other breaks
Till
between
when?
January and June. Well, there over the summer, I'm already allocating time to a different research effort with some other colleagues, so I'll probably be tied up during then.
Okay. Well, I might fire you a request to make a particular type of power supply and see if you can think you can make it. And I'd be happy to support that. But thank you. It's been really great to have a chance to share this data, although I'm missing most of it. Um,
Oh, it's so interesting. So,
yeah. Yeah. I hope the videos are there. If not, the electrode isn't going anywhere. It's going to say the same thing tomorrow as it did yesterday. Um, it's really special, and I'm going to talk about this on um, Saturday
okay,
in a live stream, and I think
excellent.
it brings together the etheric matter, this third component of um, the radiant energy, this third component of the hidden, what they call the hidden energy within matter,
Right.
um, transmutation, cold fusion, ball lightning Tesla, it gives him credit, although he didn't have the tools to know he was transmuting matter. But
With
he
the
was,
conception that in the 1890s, he was essentially practicing this.
yeah,
And I think that up until now, no one else has duplicated this type of tube or really advanced it any further. It's a shame, but I mean, it's about time. That's the way I see it, at least.
yeah, well done. Well done.
Thank you.
Have a great day.
No, you too. I look forward to talking to you soon.
Cheers. Bye.